Okay, so lesson 8.4, integrating using partial fractions. We're going to cross out some things you can see in this little box. I crossed out rule B, crossed out any mention of quadratic factors. That's wonderful news. We're working with rational functions, one function divided by another, and in particular, we're going to integrate them. And you might guess that sadly you won't be able to just do a simple u substitution and choose that for your denominator and be done. What you are going to want to do in a very plain and simple sense is break a fraction into a sum of two other fractions. Maybe then that will be easier to integrate. Look, cutting to the chase, look off to the right-hand side here. Here's 5 over 6. What we're getting at is maybe, just maybe, we could break this up into two different fractions that are added together. You look at that denominator of a 6, and you might think, well, wow, 6 is factors of 2 and 3. Maybe some fraction over 2 plus another number all over 3 would add up to 5 over 6. It wouldn't take you too long to realize it's just 1/2 plus 1/3. So that number, 5 over 6, could be broken into two other fractions. Maybe that would allow us to do some extra work. Now, I do want to say, what if you had something like 1 over 4? Notice the difference. 4 is really 2 squared. This is 1 over 2 squared. A lot of times kids might say, well, what would you have to do? We could look at this as a over 2 or b over 4. Sometimes kids look at that and they're almost like, well, why is that? Well, if I have 1 all over 2 squared, I could have a factor all over 2 to the first and a factor all over 2 to the second. By way of comparison, let's just say that I gave you something like 3/8. Now, 8 is really 2 to the third. To effectively write this out, we'd go a all over 2 to the first, b all over 2 to the second, c all over 2 to the third. Why do I bring that up? It's going to be an issue with repeated factors. And, right now we're looking at everything spelled out numerically. What we're about to do is look at things algebraically. So I hope this was a sufficient little introduction to what's happening. Let's look at example 1. Thank goodness in AMA last year, you dealt with partial fractions. This shouldn't, if it seems oddly familiar to you, here's why. You should have done this about a year ago, close to that. Look, I don't think it would take too long for kids to look at this integral in example 1 and realize, hey, we've got some issues. We've got some problems here. How do we break this down? You could try a basic u substitution. You might even try to dabble in integration by parts. No matter what you try, you'd be frustrated. But maybe, just maybe, we could break this into a partial fraction decomposition. Say, look, we've got some fraction all over x minus 6 and x plus 2. Maybe we could write that as a over x minus 6 plus b all over x plus 2. And if we could do that, that would be delightful. That would be way, way, way simpler, wouldn't it? You could think, well, how could we proceed? Well, tell you what, now you'd multiply both sides by the LCD, by x minus 6, x plus 2. And what's going to happen is, I hope it's going to become quite evident what's going to be left. And kids, after a while, are almost like, wow, I just know what's going to happen just by seeing the canceling. The left side's the nice side. You can see that the x minus 6's and the x plus 2's go away. You just have x plus 34. Right here, you'd have an a times x plus 2. And the b over x plus 2 times that least common denominator, you'd have b times x minus 6. Now remember, our ultimate goal is to know what A and B are. If we know what A and B are, we're going to be able to take that integral, that integrand especially, and break it into two separate fractions, and maybe that will be way easier to integrate. And we look here and we think, wow, I kind of remember doing this from last year. Hopefully you remember a, a wonderful method. It's not the only method, but it's a primary method for problems like this, is to choose smart values of x to plug in. Choose smart values of x. So I heard somebody say it already. Let x equal, what do you think? 6. If you let x equal 6, what does your left side become? 6 plus 34 is 40. Now, real quickly, 6 plus 2 is 8, and you'd have 8a. But here's why we're plugging in a 6. The 6 minus 6 goes to 0, and 0 times b cancels out. See, choose something, guys, that will eliminate either your a or your b. Help yourself out. And right now, you look at that and you'd say, well, if 40 is equal to 8a, that means that a would have to equal what? 5. And look at that. You can say, well, hey, now we're moving somewhere. Go back to this, non-fractional form and say, you know what? Now I'm going to plug in another x value. What other x value do you think we could plug in? -2. You got it. The left side is going to become 32. Now your a term cancels out because -2 plus 2 is 0. 0 times a goes away. -2 minus 6 is -8. You'd have -8b. So what would b equal? B would have to equal -4. Now, guys, right now you can say, hooray, we're done. Well, last year you'd be done at this point, and thank goodness that would be it. But now I guess what I really want to point out to you guys is look what I'm circling up above. This integral is a all over x minus 5, so it's 5 over x minus, I said x minus 5, I meant to say x minus 6. It's a all over x minus 6, so it's 5 all over x minus 6. That's my first fraction. And my b value, well, that's -4. That's -4 all over x plus 2. So this really ugly integral that we began with, the one where we'd say, wow, I just don't know where to start. If you do a decomposition, if you'd say, well, maybe I can find two separate fractions that would be equivalent, maybe this integral now will be way, way simpler. And I hope you'll see that it is. Now look, as we have to finish this up, sometimes kids will say, okay, well, I'm sure glad that we got to here. This does look way better. And by the way, I do want to state the obvious that you could have 5 over x minus 6 dx minus the integral of 4 over x plus 2. You could turn this into two separate integrals. That's the whole plan. But help me out. What do you think that first integral is? 5 all over x minus 6. Any guesses? 5 ln of the absolute value of x minus 6. Now, sometimes kids look back on that and they'll say, now, wait a minute. I thought I'd always have to do a u substitution to be able to do that. You could. You definitely could. But I know that you guys are well aware that the integral of 1 over u du is ln of the absolute value of u. You look at this and you'd say, well, my guess is it's 5 natural log of x minus 6. Double check that by taking a derivative. It would take you just a moment to do that. And you get confirmation that you're right. God bless you. Well, what about the second part? What's that? Minus 4 ln of the absolute value of x plus 2. Ooh, one more thing that we're going to need. A plus c. And we are done. Yes?
I'm still kind of confused why it's okay to split the denominator into a over plus b.
Okay, why is it okay to separate it? For the same reason that if I'm giving you a fraction, is it okay to separate? Could you say, are there two fractions that would add together to get the original form? So it's like when I'm giving you 5 over 6, I'm saying, is there some a over 2 plus b over 3? Imagine it was really 5 all over 2 times 3. Could I find like an a over 2 plus b over 3? That would make that true. You see what's happening? Now you can say, well, you don't see a 2 times 3 down there. Well, kind of you do with that x minus 6. X minus 6 is really just a number, right? X minus 6, whatever value of x is, it's some number. Maybe it's 2, right? And whatever, x value it is, you plus 2, it's some other number. So it's going right back up to here. 5 over 6 equals a over 2 plus b over 3. So that's why we're allowed to do that. Does that make sense? All right. Well, let's keep going for example 2. For example 2, I think it's pretty obvious that this one's a little bit messier, isn't it? Suffice it to say you might want to try a u substitution. I think you'd quickly see it doesn't work. So instead, dare I say, maybe you'd like to start factoring the denominator. That's the big difference that we're seeing in example 1. It's seeing those two separate factors that will lead us to say maybe I can break this into separate fractions, right? So what would you factor out of x to the third minus 4x squared? You'd pull out what? X squared, and what's left? X minus 4, and then we'll put our dx there. Now comes the real important part, okay? So the partial fraction decomposition is different right now. Sometimes kids look at this and they'll think, what's so different about it? I don't get it. It's the squaring part that you're seeing for x squared. You see that? Here's your x squared. Why do I bring that up? It's kind of like when we dealt with the 1/4 up above. The 1/4 was really 1 over 2 squared, wasn't it? Whenever you have a repeated factor, you're going to have to represent all powers of that term. So when I see x to the second, I'm going to have to say I need to consider a over x to the first plus b all over x to the second. Okay, that's something we just have to get very used to. Again, sometimes kids look at that and they're like, I don't get it. Why? The same reason that I was saying right above where I highlighted that 1/4. The 1/4, you'd want to think of maybe something over 2 and something over 4 possibly adding together. So we always have to represent that. And like I was saying, if you had 1 over x to the third, then you'd need a over x, b over x cubed, x squared, and then c over x cubed. Every power of that factor would have to get represented. But then we're going to say plus c over x minus 4. Tell you what, at this point, I'm going to stop the video.